So let's work with this example. We're going to use the Gauss-Jordan method to determine whether the following system has no solution, a unique solution, or an infinite number of solutions. Okay, so the first thing we're going to do is to write the augmented matrix for this problem. So in this case, we have 1 for the first equation, and then 2. We have 0, -1, 2, and 3. And we have 0, 1, 1, and 3. Okay, so this is the augmented matrix. 1, 1, 0, 2, 0, -1, 2, and equals 3, and then 0, 0, 1, 1 equals 3. So we are going to perform some elementary row operations now. We want to make sure that we create an identity matrix towards the left of this augmented matrix. And then once we have completed that process, then we'll get the final solution. So as you can see in this example, if you look at that first column, the format of that column is already in the format that we wanted. So 1, 0, 0, that's the first column of the identity matrix. So we don't have to work with that column. So this column is good. So now I'm gonna move to the next column. And in this case, I wanna make this number equal to +1. And then the other two values in that column, this one and this one, they have to be equal to 0. So in order to make that value equal to 1, I'm going to multiply that row times -1. And the result is the following matrix. We'll have 1, 0, 0, 1, 1, 1, 0, -2, 1, and then 2, -3, 3. So by multiplying that second row, this is by -1, this is the resulting new row. Okay, so now I'm gonna work with this one here. I wanna make that equal to 0. So what I'm going to do is I'm gonna multiply this second row by -1. And then I'm going to add that row to, row 1. So the resulting new row after performing that, so I'm multiplying the second row times -1, and then I'm adding that row to row 2 to row 1. So in that case, we get the following. It's 1, 0, 2, and 5. And then the rest of the matrix is the same. 0, 1, -2, and -3. 0, 1, 1, 3. So this is the result of multiplying that row, that second row, and by -1, and then adding that to row 1. So let me make that here. So this is the result. So now we're good. Now the next step is to make this value equal to 0. So to do that, I'm going to multiply or perform the same operation. I'm going to multiply that second row by -1, and then that add to, so I'm going to multiply this by -1 and then add that to row 3. So the resulting matrix is here. We'll get 1, 0, 2, 5, and then 0, 1, -2, -3. So that's the same. So what's going to change is the next row. So -1 times 0 plus 0, that's equal to 0. -1 times 1 is -1 plus 1, that's 0. -1 times -2 plus 1, that's equal to 3. And -1 times -3 is 3 plus 3, that is equal to 6. Okay, so we have completed that process for row or the second column. So now we have to work with this column. So we are gonna wanna make this value equal to 1. So to make that happen, we're gonna multiply that row times 1/3. And the resulting matrix is the following. So the first row stays the same. Second row stays the same. And then we multiply that third row by 1/3. So this is 0, 0, 1, and 2. Okay, so we now have to work with this value. We need to make this equal to 0. So we are going to multiply this by 2, and then we're going to add that to row 2. Okay, so the resulting matrix is the following. We get the first row stays the same. So this is a 2. Fix that. This is 2. And then the second row stays the same. So 1, I'm sorry, the second row will change. Now we are multiplying 2 by the third row and adding to row 2. So this is going to be 1. This is going to be 0. And this is going to be equal to 1. And then we have 0, 0, 1, 2. So the last one is the making this equal to 0. So we are going to multiply now this times -2, and we're going to add it to row 1. So this was to get to this point, and this was to get to this point. And then the values for that one will be 1, 0, 0, 5. Sorry, 1, 0, 0. This is 1. Since you multiply this by -2 times 2, that's -4 plus 5, that's 1. So this is 1. Then we get 0, 1, 0, 1, and we get 0, 0, 1, 2. Okay, so at this point, we have completed the process. And the question now is, what is the solution? And if the solution is unique, or we have an infinite number of solutions, or if the problem has no solution. So this is the solution that we get. X1 equals 1, X2 equals 1, and x3 equals 2. Since there's all of them are based on our previous discussion, these decision variables, all of them are basic. There's no non-basic variables in this matrix. So, and then if you look at the rows, there's no 0 rows. So that means that this solution is unique. All of the decision variables are basic. So we get a solution for this set of linear equations equals x1 equals 1, x2 equals 1, x3 equals 1. So if you substitute that into this group of equations, you should get the same values on the left. So 2 equals 2, 3 equals 3, and 3 equals 3. Good. So now we are going to move to discuss the concept of linear independence and linear dependence. So in order to start the discussion, we're gonna let V equals a row vector with coefficients V1, V2, Vk, all having the same dimension. So V is a set of row vectors. So each V1 is a row vector, V2 is also a row vector, and so on. A linear combination of vectors in V is any vector of the form C with Z is a coefficient, 1 times V1 plus C2 times V2, and so on, where C1, C2, and CK are arbitrary scalars. So for example, if we have the following set of row vectors, like the one we have here, if we multiply that by 2, and then if we multiply 2 times V1 and then subtract V2, this is the resulting vector. It's 2 times that row vector 1, 2 minus 2, 1, which is vector 2. So forming this multiplication, we get the following. We get 2, 4 minus 2, 1. And that is equal to 0, 3. And if we do the same thing here for V1 plus 3 V2, we get the 1, 2 plus 3 times 2, which is 6. And 3 times 1 is 3. So if we do the summation for that, we get the following: 1, 2 plus 6, 3, that's equal to 7, 5. A set of vectors is called linearly independent if the only linear combination of vectors in V that equals 0 is the trivial linear combination of having all arbitrary coefficients or scalars equal to 0. So if the only way that you can make that equal to 0, if the only way that you can make the linear combination of vectors in V equals to 0 is by multiplying those vectors but these coefficients equal to 0, then those vectors are called to be independent. A set of vectors is called linearly dependent if there's a non-trivial or non-trivial linear combination of vectors in V that add up to 0. So for example, show that V, this set of linear vectors, row vectors 1, 2, and 2, 4 is linearly dependent. So if we can find a non-trivial linear combination of vectors that add up to 0. If that's the case, then we can say, or we can confirm that this is a linearly dependent set of vectors. So since we know such combination exists, so for example, if I do 2 times this row vector 1, 2 minus 1 times 2, 4. If I do that, if I arbitrarily select minus 1 and 2 and perform this operation, I can obtain a vector that is equal to 0, 0. So since there is a non-trivial linear combination with coefficient 1 equals 2 and coefficient C2 equals minus 1, that yields 0, then we know that this is a linearly dependent set of vectors. Thus, V is a linearly dependent set of vectors. So what does that mean? What does it mean for a set of vectors to be linearly dependent? If a set of vectors in V are linearly dependent, the vectors in V are in some way not all different vectors. The direction specified by any vector in V cannot be expressed by adding together multiples of other vectors in V. So for example, in 2 dimensions, 2 linearly dependent vectors lie on the same line, like this example. These vectors are linearly dependent. Whereas if that is not the case, then we have linearly independent vectors. So these 2 vectors are pointing in different directions, whereas for linearly dependent vectors, we have them pointing in the same direction. The rank of a matrix is an important concept also in terms of linear independence and linear dependence. Let A matrix be any m times n matrix and denote the rows of A by R1, R2, Rm. So we can define also R as a set of vectors R1, R2, up to Rm. The rank of A, which is a matrix, is the number of vectors in the largest independent subset of R. So how to find the rank of a matrix? We can apply the Gauss-Jordan method to matrix A. Let A prime be the final result. It can be shown that the rank of A prime is going to be equals to the rank of A. So the rank of A prime is equal to the number of non-zero rows in A prime. Therefore, the rank of A, which equals the rank of A prime, is the number of non-zero rows in A prime. So let's look at this example. So we want to find the rank of V. V is a set of vectors, row vectors. So V is has 3 row vectors here. So those 3 row vectors form this matrix A. So we want to see, or we want to compute the rank of this matrix A. So as discussed in the previous slide, we can apply the Gauss-Jordan method, and then using the final result, which is here, we can determine the rank of the matrix by looking at the number of non-zero rows in this A prime matrix. So we go to the next slide. A set of vectors V is linearly dependent if the rank of A is less than M. So coming from that previous example, determine if the set of vectors is linearly dependent. So we want to know if this set of row vectors are linearly independent. So after performing the Gauss-Jordan method, we get these A prime. We can see that there's a rows of zeros here, and we want to count the number of non-zero rows. So in this case, we have 2. So that's the rank of A prime. So the rank of A prime equals 2. So now using that information, we want to check, and remember that M is the number of rows. We want to verify if this set of vectors is linearly dependent or independent. So using this statement, since the rank of A prime equals 2, and we know M, which is the number of rows, equals 3. So an M equals 3, and we know that the rank of A prime is less than M, then the set of vectors, then the set of vectors in B are linearly dependent. The next concept is the inverse of a matrix. A square matrix is any matrix that has an equal number of rows and columns. The diagonal elements of a square matrix are those elements aij, such that I equals j. So the location of I equals the location of j. So it's that diagonal of the matrix. A square matrix for which all diagonal elements are equal to 1 and all non-diagonal elements are equal to 0 is called the identity matrix. And here we have I3, which is an example of a square matrix with diagonal elements equal to 1 and the rest equal to 0. So this is an identity matrix with M equals 3. For any given M times M matrix A, the M times M matrix B is the inverse of A if we can multiply matrix A and B, and that will give you the identity matrix. Some square matrices do not have inverses. If there's not thus exist an M times M matrix B that satisfies B times A equals A times B equals to the identity matrix, then we write that B is the inverse of matrix A. So for example here, we get matrix A, which has 3 rows and 3 columns. So it's a square matrix, 2, 0, minus 1, 3, 1, 2, minus 1, 0, 1. And we can find a matrix B that when multiplied by A is going to give us the identity matrix. And such a matrix is this matrix 101 minus 5 times 1 minus 517 and 102. Just to double check, this is the multiplication, A times B. And after completing this multiplication of matrices, then the result is this identity matrix. Why are we interested in the inverse of a matrix? Suppose we want to solve a linear system of equations AX equals B that has M equations in M unknowns or M variables. Suppose that that inverse A minus 1 exists. The results of multiplying both sides of the equation by A inverse is the following. So if we multiply A inverse by AX and by B, then the results is equal to the identity matrix on the left times X equals A inverse times B. So basically what we are saying is that we can obtain, by knowing the inverse, we can obtain the solution for the set of linear equations very quickly. This shows that knowing A inverse enables us to find the unique solution to a square linear system of equations. The Gauss-Jordan method may be used to find A inverse or show that A inverse does not exist. So for example, using the Gauss-Jordan method to find A inverse, given matrix A, create the augmented matrix A I2. So we're basically adding this identity matrix to the right of this matrix. That's the augmented matrix. So the idea now is we are going to use the Gauss-Jordan method to make this side of the matrix the identity matrix. So to transform A into I2 using the elementary row operations, that's the steps that we are going to follow now. We can multiply that first row, this first row by 1/2, and that's what we are seeing here. So it's the whole, the whole row that we are multiplying by 1/2. And then we continue the process until we get to find this identity matrix on the left. So what we have on this side is what is the A inverse. Okay, so that's our inverse for the original matrix. So we can use the Gauss-Jordan method to find the inverse of a matrix. Some matrices do not have inverse. So for example, consider matrix A. After applying the Gauss-Jordan methods, this is what we get, or A prime. So matrix A does not have a solution since the bottom of row A prime has zeros, as we discussed earlier. This can only happen if the rank of A is less than 2. If M times M matrix has A has a rank that is less than M, then my A inverse will not exist. Use matrix, in this example, we're gonna use the matrix inverses to solve linear systems. So we have this set of equations, 2 equations here. And we want to find the value of x1 and x2 that will satisfy these 2 equations. So if we form the augmented matrix form, we have, these are the coefficients, this is the vector of decision variables, and this is the right-hand side. Since we know the value of the inverse, we found that on the previous example. So if you know the inverse, then you can use the information from the inverse to find the solution for this set of equations. As we stated earlier, by knowing the inverse, we can apply the inverse in this way. We can multiply the inverse times B and find the solution for the set of linear equations, or the solution in terms of X. So since we know the inverse is 3 minus 5 minus 1 and 2, multiplied by V 7, 4, then this is going to be equal to 1, 1. Thus, the solution is unique, and x1 equals 1, x2 equals 1. Now let's talk about the determinants. Associated with any square matrix A is a number called the determinant of A. So let's use this matrix A to illustrate this. So A11, A12, those are the locations ij. So in this case, I equals 1, j equals 1. In this case, I equals 2, j equals 2. For a 1 times 1 matrix, the determinant A is equal to the value of A11. For a 2 by 2 matrix, the determinant of A is determined by multiplying A11 times A22 minus A21 times A12. So as the example is going to illustrate, if I want to find the determinant of this square matrix, this is going to be equal to A11 times A22. So in this case, this is 2 times 5 minus 3 times 4. And this is equal to minus 2. See, if A, which is the matrix, is an M times M matrix, then for any values of I and J, the ij minor of A, which is the matrix, is the M minus 1 times M minus 1 submatrix of A, obtaining by deleting row I in column J. So if we have this matrix and we want to find the minor of A for 1, 2, then we are deleting row 1, and we are also deleting column 2. So the resulting A1, 2 is 4, 7, and 6, 9. If we do 3, 2 is the same thing. Let me delete this. So for 3, 2, we delete row 3, column 2. So the resulting minor matrix is 1, 4, 3, 6. 1, 4, 3, 6. Let A be any M times M matrix. We might write as A as follows. This square matrix with all these coefficients. So in this case, we have a big matrix. So to compute the determinant of A, pick any value of I equals 1, 2, up to M. And then the equation will be as follows. Determinant of A is going to be equal to, so I values are really important now, minus 1 to the power of I plus 1, AI1, the determinant of AI1, plus the same expression, but now we are adding 2 instead of 1. And then we continue incrementing that value as we increase the value of m. So in this case, this is 2, this is 2. In this case, this is m, and this is m. The above formula is called the expansion of determinant A by cofactors of row I. So for this example, here we have a 3 by 3 matrix. Let's find the determinant of A given matrix A. So the determinant of A is expanded by using row 1 cofactors. Row 2 or row 3 could be used with similar results, but in this case we use row 1 cofactors. Notice that using row 1, A11 equals 1, A12 equals 2, and A13 equals 3. And the minor matrix are the following: A11, 5, 6, A9, A12, 4, 6, 7, 9, and A13 are 4, 5, 7, 8. So the determinant for each one of these cases are as follows. So the determinant of A11 will be equal to 5 times 9 minus 8 times 6. And this is equal to minus 3. The determinant of 1, 2 equals 4 times 9 minus 7 times 6. And this equals minus 6. And the determinant of A13 equals 4 times 8 minus 7 times 5. And this equals minus 3. So the determinant of A in this case will be equal to 1 times 1. Sorry about that. Times minus 3 plus minus 1 times 2 times minus 6 plus 1 times 3 times minus 3. And this is going to be equal to 0. So this makes sense since the set of row vectors forming matrix A are clearly linearly dependent. So when that's the case, then we should get a determinant that is equal to 0. So this is the last slide, and this is going to complete our lecture on the review of linear algebra. And these are the topics that we cover: matrices and vectors, matrices and system of linear equations, the Gauss-Jordan methods for solving systems of linear equations, linearly independence and linearly dependence, the inverse of a matrix, and finally, the determinants.